We're learning about average rate of change in this video. We'll also contrast it to something that's going to appear properly in the next video, which is instantaneous rate of change. And a little bit of contrast will happen in this video, but more of that will happen in the next video. Contrasting the two, the average and the instantaneous, basically helps us understand each of them. And the example we're going to use first up relates to distance, time, and speed. It's a good one to start with because most of us can relate to this. In a lot of cars, we have two ways, or two devices, or two instruments that can describe speed to us. So in the first diagram there, you can see the dial of the red bezel around it, and that's a speedometer, as you know. And it looks at the instantaneous rate of change. So it looks at the instantaneous speed of the car, or the velocity. And below we've got a readout which has things like average MPG, average MPH, and so on. That's a trip computer. And even though in Australia we use kilometers per hour, miles per hour, MPH, is a unit of speed used in some countries still. And miles per hour is a speed, so average MPH is the average speed of the journey. That is different to the instantaneous. So typically, most of the time, the speedometer needle is changing its position, whereas the average speed will be calculated at the end of a journey. So it summarizes, the average summarizes, whereas the instantaneous gives us a report every moment of the velocity or the speed of a vehicle. To our left, we can see a graph of distance in meters versus time in seconds. And we have two scenarios. We have a car, let's call it the red car, and the blue car. And they've basically gone the same distance over the same time. But the graphs are different, and their journeys have been different. The red car basically has moved at a constant speed, and just maybe an open road without any interruptions, and it stayed on 60 kilometers per hour for 60 seconds. And it's very easy to work out the average speed. So the average speed is distance traveled over time taken. This is very easy to see because the speed didn't fluctuate. So putting the calculations in, 1000 divided by 60 is 16.6 recurring meters per second, which we can convert to 60 kilometers per hour. Pretty obvious because the red vehicle's speedometer needle would have stayed on 60 over that whole period of 60 seconds. So it would have easy to see. So what about the next one? We see a blue car with it's been stuck in traffic, perhaps like in the photograph below there, and we can see that the speed was fluctuating. So that blue car took its journey for the same amount of time, but you can see that it never got to the same distance. It never traveled as far because it was going slower because it was stuck in traffic perhaps. So its instantaneous rate of change, or its instantaneous speed, changed. You can tell that by the slope of the graph changing as you look across the blue line, different to the red line. And of course, just by directly reasoning with it, if they both went for 60 seconds, one only covered 300 meters, the other one covered 1000 meters, the blue one is therefore going slower on average across the journey. Let's have a look at that. Using the same formula above, the average speed would be 5 meters per second, or converted 18 kilometers per hour, somewhat slower, only about 30% of the speed in fact on average. But we can see that doesn't mean the speedometer stayed on 18. There would have been times when it was above and below that. We can look at points B and A there to show that. So in the purple writing there, we have up to point A, the average speed was higher then this overall average for the whole journey, it's 24 kilometers per hour. So it was going on average a bit faster in the initial part of the journey. Now let's see up to point B how quickly it was going. So I'll put that in red. So its average speed was 6.6 recurring meters per second, or 24 kilometers an hour as well, which means it must have slowed down when we were going from B to C to bring the average down to 18. So in the dark brown, I've calculated it from B out to C, and the average was 12 kilometers per hour. So all of those averages together make 18, and so that's quite different. Even though they've gone for the same amount of time, the speeds are different, and it just goes to show that once we stop moving at a constant speed, calculating the average rate of change becomes complicated. And while it can be a reasonable summary of a journey, it might not represent some parts of the journey very well at all. So it has some limitations to it, the average rate of change. So the calculations are straightforward, but the accuracy or the appropriateness of it varies. In general, when we're looking at the average rate of change, in particular the average speed, what we do is we look at 2 points, and if we want to know the average rate of change, or that in this particular case of distance and time, the average speed between points P and Q, we mark on the curve, the red curve P and also Q, and we draw a straight line that connects them. Now that straight line is called a secant. It's important to know. So the line itself, the blue line, is called a secant, and it's a straight line that connects 2 points on a curve. The part that is within the two given points, this bit here, that is called the tangent. The chord, sorry, not the tangent, the chord. Sorry, tangents will come up in the next video. I was getting ahead of myself there. So that is a chord, just like you would have seen when you studied circular geometry. So the whole line is called the secant. The part that's just bounded by the 2 points P and Q is called a chord. So a secant is basically an extension of a chord. It's important to make note of those two bits of terminology. Now before we go into the formula, you can see that the actual all of the speeds that this object is going at changes, because you can see that the slope of the red line is changing all the time, and you can see that there's a gap there between the red and the blue. So the chord is only a summary, or the actual average rate of change line is only a summary of what's going on as far as the speed goes. In general, the average rate of change over the interval AB, so if we're looking at interval AB, which you can see there on the x-axis, if we're looking at the average rate of change, we need to have the coordinates of A and B. Now in general, we would call that, because on the x-axis it's denoted as little a, and that would be f of a, we sub it into the function, and this would be b, and that would be f of b. We would have f of b minus f of a over b minus a. Now that should ring a bell, because it links, not unsurprisingly, links to other things. We were going average speed before, which is the distance travelled over the time taken. Alright, so basically it's the difference in that quantity divided by the difference in that quantity, and that should also ring a bell in terms of your previous work on gradient, which is the symbol m, and it's the rise over the run, or y2 minus y1 over x2 minus x1, or in other words, the change in y over the change in x, which is sometimes written as delta, that's what that triangle is, delta y over delta x. So really this is just an application of the gradient which we saw in the previous video. So that's what we do. That's your average rate of change formula. Let's look at an example. So here's an example. The air temperature, capital T, degrees Celsius at a weather station on a particular evening, modelled by that equation given there, where little t is the time in hours after 6 p.m. So with questions like this, just make sure you've read that last bit. T is the time in hours after 6 p.m. It's not starting at midnight like some models do. So you are welcome to draw a graph either by hand or probably with graphics calculator or software. So there we are. We've got the graph of the temperature versus time. Now it was between 6 p.m. and midnight, so where my cursor is, that's 0 on the horizontal axis. It's in line with that, so that represents that anywhere on that vertical line represents 6 p.m. and midnight is 6 hours later. So we go out to the 6 here, and you can see that's the extent of the interval there where you see the cursor move. So we write our formula down. So for the temperature, the average rate of change okay, that equals, we've got a capital T is the output or the dependent variable. So we've got T of 6 minus T of 0 over 6 minus 0. So we need to find T of 6 and T of 0. So it's best if we do that algebraically. So T of 0, write that in. So we've got 600 over 0 plus 0 plus 30, which is 600 over 30, which is 60 over 3, which is 20 degrees Celsius. And I've just done the same for T of 6, so we sub 6 in, and we get about 7.69 degrees Celsius rounded to 2 decimal places. Subbing that into the formula, 7.69 minus 20 over 6. It's clearly going to be negative rate of change. So the temperature on average has dropped. We get negative 2.05 if we calculate that. Now, rate of change, what's the unit? So it's rise over run. So it's degrees Celsius per, or over, degrees Celsius per hour. So negative 2.05 degrees Celsius per hour. So that's the rate at which the temperature dropped in that interval on average. So there's our average rate of change. The next video will be contrasting this with instantaneous rate of change and some of the complexities that pop up while we do this.